All right, so just in case we don't get to some of these in class, I figured we should probably go over the review here. So you've got a test coming up. Here we go. So number one, just ask which of the following are examples of acceleration. So remember, acceleration is, by definition, a change in velocity. Well, technically, it's the rate at which your velocity changes, right? But you've got to be changing your velocity. And so for that to happen, you've got to do one of three things. You got to speed up, you got to slow down, or you got to turn. So an object is accelerating if it's doing any one of these three things. All right, if you're doing any of those three things, you are accelerating. So a car drives straight south, not turning. Constant speed, not speeding up or slowing down. So this one is not an example of acceleration. In B, a car drives at a constant speed. Don't let that throw you off. It is a constant speed. It's not slowing down or speeding up, but it is going around a curve. So B is an example of acceleration. In C, the car is stopping, which is a way of slowing down. So that is accelerating. In part C, you're going from a stop sign and then speeding up. So that is an example of acceleration. And then finally E, if you drive a car off of a cliff, there's all kinds of problems there. Here's the car. Hello. Right, so the car drives off the cliff. A couple things are happening. One, after it goes off the cliff, it's going to speed up because it's falling, right? Gravity's going to pull it down. It's going to go faster and faster. Also, you can see the path that it follows is not a straight line, so it's turning. So that is super accelerating. All right, there we go. All right, number two. So we get a car that's accelerating. So let's start by making a drawing. So here is our drawing. Here's our car. He's very happy to be a car. He's going from rest up to 8.7 meters a second. So the car drives to over here. Still very happy. Hello. And he's going at 8.7 meters a second. And it tells us that all throughout this, our acceleration is 3.1 meters a second squared. All right, we should take a minute and check our signs. So at time zero, our velocity zero, there's nothing there. Over here, our velocity is going to be positive because the car is moving in a positive direction. Remember, the sign on your velocity is determined by the direction you're moving. All right, and then the acceleration has got to be positive because the velocity here is increasing, right? It's going from 0 up to 8.7. And that means that our acceleration has got to be positive. All right, so with that in mind, in part A, I can find out how long it takes for this to happen. So I can use the x, right? T equals VF minus VI over A. So let's see, our final velocity is 8.7 meters a second. Our initial velocity was 0. Our acceleration is 3.1 meters a second squared. So divide it out and you get 2.8 seconds, as is on the answer key. All right, so that is that. So let's get this stuff. Whoa, that is not at all what I wanted to happen. All right, so there's part A. I kind of shrunk it over here in the corner. Hello. All right, part B says, how far will the car go? Oh, well, this is the same exact time interval. So, right, because it's talking about, when it says this time, it means this time here in the 2.8 seconds. So when I say how far does it go, that means we're looking for displacement. So you can use any of the displacement equations. You guys seem to prefer the screwdriver, so here we go. VF plus VI, half of that times your time. So my VF is 8.7. Oops, skipped a step. So 1/2 times our VF, which is 8.7, plus our VI times our time, which we just found to be 2.8 seconds. So multiply all of that out, and you get 12.2 meters. Okay, so that one is just kind of a plug and chug deal, all right? The important thing there is that I did pause and think about my time interval, right? I didn't just dive in blindly and go, oh, the time is 2.8 seconds. The problem very specifically says in this time interval, which is, indicating that it means the same time interval that we had been talking about previously. Now, in part C, this is where people always get tangled up. Part C says, how fast is the car going when it has traveled 8 meters? Well, look, the 12.2 meters is the displacement that it has traveled to when it gets to right here, right? Right? Because everything that we've talked about here has been during those 2.8 seconds that it took to get to this velocity. All right? So for question C, I want to know how fast is it going when it's gone 8 meters. So there's going to be some point in here, maybe it's here, and at that point our displacement is 8 meters. And our question is, what's the velocity at that point? So we're looking at a new time interval now. Question C wants to know the final velocity at the end of the time that it took to go through a displacement of 8 meters. So my displacement goes from here to here. So for part C, you're going to start, as always, by writing down what you know. So here's what we know. I know that my initial velocity is 0. I know that my acceleration is still 3.1 meters a second squared. I know that my displacement is 8 meters. And I'm looking for my VF. So we've got to pick an equation that uses all four of the, well, not uses all four of those variables, but those are the variables we have to work with. So I noticed that I can't find the time, that I don't know the time, and I don't see an easy way to find it. So when that happens, you should look in the direction of the vice grip. And the vice grip tells us that we can find VF by doing the square root of 2 times the acceleration times the displacement plus the VI squared. So let's do that. So you're going to get 2 times 3.1 times 8 plus 0 squared, and square rootify it. And you get a final velocity of 7.0 meters a second, or pretty close to it. All right, so there we go. So that's how you do part C. Move this out of our way. Clear up some room. Oh no. All right, and then finally, question D. D says, how long would it take the car to travel the first 9.5 meters? So now we're looking at another displacement, so maybe that's here, where our displacement is 9.5 meters. All right, and we're trying to find the time. So it looks very similar to the last problem, except instead of looking for the final velocity, we're looking for the time, right? Check it out. We know that our initial velocity is 0. We know our displacement is 9.5 meters. We know our acceleration is 3.1 meters a second squared. This time we're looking for time. And so our problem is the only time equations we have are, well, we got the x, but that doesn't help us at all because I don't know my final velocity. We've got the screwdriver. I almost never use this one. But it's 2 times the displacement over VF plus VI. And I think that's it. So we're kind of stuck. So when this happens, we can't find the thing we're looking for. Let's find something else. Right? So I notice that I don't know my VF. All right, so what we're going to actually end up doing here is we're going to use the vice grip. We're going to use this equation again to find our VF. And then once we've got our VF, we can plug it in here and find our time. So that's the process that you have to go through. All right, so if you do that, I'm a little bit out of room here. Oh, well, duh. Look at all the room I have. So when you do that, let's see, VF is going to be 2AD plus VI squared. Don't forget to square root it. So you get 2 times 3.1 times 9.5 plus 0 squared, square rootified. And you find that your VF is, so that gives you 7.7 meters a second. And now you can find the time by plugging that in up here. So you get a VF of 7.7 meters a second minus 0 all over 3.1 meters a second squared. And it gives us whatever we said the time was, 2.5 seconds. All right, so there we go. All right, next, number 3. says, suppose I told you that an object accelerates at negative, so A, acceleration is negative 4.5 meters per second squared. So before I answer question A that says, what does it tell you? Just remember, this is the same thing as negative 4.5 meters per second. Okay? All right, so I just had to pause that there for a minute. So let's see, where was I? So remember, your acceleration can be written as meters per second per second. So what does it mean? Well, it means that, first of all, this is negative. That means the velocity decreases by 4.5 meters a second every second. 3-point question on the test. Should be the easiest question on there because it's the same answer every time. The only thing that can possibly change is this word might not be decreases. If your acceleration is positive, it'll be increases. And then obviously the number is not always 4.5. All right, so there you go. All right, so let's fill in a little chart here. So the idea is our velocity starts at 20.5, and then every second it goes down by 4.5. So I'm going to just literally keep subtracting 4.5. So you're going to get 16, and then you're going to get 11.5, and then you're going to get 7, and then you're going to get 2.5, and then you're going to get negative 2, and negative 6.5, and negative 11, etc. The acceleration, there totally isn't room here, but these accelerations are all negative 4.5 meters a second squared. All right, and then your direction of motion depends on if the velocity is positive or negative. So positive would be east. So we're going east, because these are all positive velocities until we get to here. Now the velocity is negative, so now we're going west. All right, so there we go. All right, and then finally, how far will the object move in the first 2 seconds? Well, you got a bunch of choices. In the first 2 seconds, for C, in the first 2 seconds, our velocity is going from 20.5 meters a second to 11.5 meters a second in a time of 2 seconds with an acceleration of negative 4.5 meters a second squared. So find your displacement, right? So you got your pick. You guys like the screwdriver? Let's do it. Vf plus Vi times T. And so you're going to get half of 20.5 plus 11.5 times 2. And so it just gives you what? 32 meters, right? All right, so that's that guy. Number 3, what's the acceleration? Well, what's the velocity doing every second? Let's see, it goes up by 3. Notice it's up by 3. It's getting less negative. Up by 3, up by 3. Let's see, it's always going up by 3. That means my acceleration is 3 meters per second. Or you can just write 3 meters per second squared. Either one is totally cool with me. All right. I guess I could have full screened this, right? All right, let's see, what else? All right, number 5. Oh, look at this. Speedy drives straight north at a constant speed of 31 meters a second for 27 seconds. Well, going 31 meters a second means exactly that. You're going 31 meters every second. So that's my velocity. Notice it's constant. And then my time that this occurs for is 27 seconds. So to find my displacement, it's just velocity times time. We're going 31 meters a second for 27 seconds. So multiply that out and get 837 meters. All right, and then what's the acceleration? Well, acceleration is Vf minus Vi over t. But my velocity is constant. It's always 31. So I'm going to get 31 minus 31 over 27. I'm going to get 0. Well, of course I'm going to get 0 because constant speed means that I'm not speeding up or slowing down. I'm going straight north, so I'm not turning. So my velocity is not changing. I'm not accelerating. All right. Next guy, bowling ball rolling up a hill. All right, so here we go. This is one where you got to make a drawing, right? Here's our hill. The ball is going to start with a velocity here of 9.2 meters a second. It's going to go up the hill and come back down. And then the problem tells us that the acceleration the hill gives the ball is 2.3 meters a second squared. Remember though, my velocity's got to decrease. As the ball goes up the hill, it's going to slow down until it stops. So my velocity's got to decrease, which means this acceleration is negative. That is one of the most common mistakes. Negative because v is decreasing. I see people make that mistake all the time, and if you leave those negatives out, all your answers are going to be wrong, which is obviously bad. All right, so let's see, how far does the bowling ball go? Well, so for A, we want to figure out how far it goes before it goes back down the hill. So question A, all right, trying to decide what color I want to use here. Question A wants to know how far it goes from here to here. So for part A, my initial velocity is 9.2 meters a second. I want to know how much the displacement is in the time that it takes to get to a final velocity of 0 if the acceleration is negative 2.3 meters a second squared. So the big thing is this hidden 0. We're trying to find the displacement until it gets to the top, and at the top the velocity is 0. So use your vice grip. Your displacement then is vf squared minus vi squared all over 2a. So plug in your numbers. You got your vf, your vi, your a. You can just plug your numbers in. And you get 18.4 meters. All right. So that is that. Oh, I did it again. Darn it. All right, so I sort of moved A up out of the way. All right, question B says, when is the ball back to its original position at the bottom of the hill? So question B wants to know, how long does it take to go from the point where he rolled it up the hill and then come back down to its final position? All right, so the big thing to remember here, there's a couple of ways of doing it. One way is to just find the time, the red time, using the information we found in A, find the time, and then double it, which totally works. But just to be clear, the other way you can do it specifically is to say, well, I know when I first rolled it, the velocity was 9.2. When it gets back to its starting spot, the velocity is going to be negative 9.2. It's the same number because the path is symmetric, or symmetrical, and then it's coming back down, so it's negative. And then you know your acceleration is negative 2.3 meters a second squared, and we're looking for the time. So it's vf minus vi all over a. Plug in your numbers, you're going to get negative 9.2 minus 9.2. That's telling me how much the velocity decreased by at a rate of 2.3 per second. Divide it out, and you get 8 seconds. Notice the negatives cancel. If you get a negative time, you made a mistake. Go find it. All right, question C is dumb. What's the acceleration after 3 seconds? Well, the acceleration is constant. So it's 2.3 meters a second squared. D, when is the displacement increasing and when is it decreasing? Well, on the way up the hill, you're getting farther from your starting point. So it's increasing on the way up the hill and then decreasing on the way down the hill. The velocity is positive on the way up the hill and negative on the way down the hill. When is the velocity increasing? Well, let's see, it goes from 9.2 to 0 and then down to negative. It's never increasing. It's always decreasing because our acceleration is, negative. I made a mistake, didn't I? In C, what's the acceleration? It should be negative 2.3, right? And that was what we'd used here, and it's what we used here, and it's what we used over here. All right, so that's the deal. All right, number 7, another ball going up a ramp problem. I guess let's put a car in this one, right? Let's lock this so that it doesn't move around on me again. All right, make our drawing. Here we go. Here is our car. Happy. Going up the hill at, what does it say? 13.5 meters a second. So it's going to go up the hill, it's going to come down the hill. I know up here the velocity is 0. I know down here the velocity is negative 13.5 meters a second. And then it says after 12.4 seconds, it has come back down to its original position. So I know the time to get here is 12.4 seconds. So for part A, to find the acceleration, you just do A equals VF minus VI all over T. And plug in your numbers. Let's see, the VF is the negative 13.5 meters a second. The VI is positive 13.5 meters a second. And that all takes 12.4 seconds. So divide it out and you get negative 2.18, negative 2.2, however you want to do it, meters a second squared. We'll be sloppy about our significant digits. So that's that. B, what does it tell us? Well, velocity decreases because it's negative. The velocity decreases by 2.18 meters a second. Every second. All right, hopefully you guys have got that down by now. All right, let's clear up some space on the board here, and then I think after we finish this problem, we're gonna have to stop here because I gotta go feed my kids. What is going on? And so I will make a second video that has the graphs. Oh, darn it. All right, I'm going to just erase. So here we go. Okay, so C, how far will the car go up the hill? So we're trying to find the displacement from here to here, right, for C. So VI is 13.5 meters a second, VF is 0, acceleration is negative 2.18 meters a second squared. We just found that. We're looking for our displacement. So use your vice grip, VF squared minus VI squared all over 2A. And we know all the numbers, so you just plug them in. So you're going to get 0 squared minus 13.5 squared, divide by 2A, your negatives cancel, and you get 41.9 meters or somewhere in that neighborhood. Now, depending on how you round, because I'm sloppy about my significant digits, you might get a little bit more or a little bit less, and that's fine as long as you're in that neighborhood. Okay, cool. Now, D, new time interval. Question D says, how far up the hill is the car when it's rolling at 4.1 meters a second? So the idea is somewhere in here there's a point where the velocity is 4.1 meters a second, and I want to know the displacement to there. So for D, you solved it the exact same way as you just did C, except your final velocity is not 0 anymore. Oh, my voice just cracked. Your final velocity is not 0 anymore. It's now 4.1, right? So let's do it. So question D, VI is still 13.5 meters a second, but now I want to find the displacement that we get to in the time it takes to get to a final velocity of 4.1 instead of 0 with this acceleration, negative 2.18 meters a second squared. So just use the vice grip again, right? You don't know the time, so find your displacement. So it's VF squared minus VI squared all over 2A. Plug in your numbers, and you do get somewhere in the neighborhood of 37.9 meters. All right, and then E wants to know how far up the hill is it when it's rolling down at 4.1. So it turns out that it's at the same spot, and so you get the same answer, right? But when you calculate per E, the difference is you make your VF negative 4.1 to indicate that it's coming down. But notice when I plug it into my equation here, that's going to get squared, so the negative ends up not mattering, and you get the same answer. All right? So that is that. All right, I'm going to stop there, and then I'll also post a link for the graphs.